Producing oil and gas from the North Sea is a highly skilled operation, carried out in an environment which is often hostile. A crucial factor in continued and successful production is the safety of the personnel who operate, maintain and repair the structures and equipment offshore. Their safety can be ensured only by constant awareness of the need for cooperation and vigilance in observing basic procedures. As part of their contribution to safety, Shell UK Exploration and Production provide the MSV Staydive, a multifunctional service vessel which performs a vital role in construction, inspection, maintenance and repair work on platforms and pipelines, and is also the primary emergency support vessel in the red sector of the North Sea, the sector for which Shell Expro is the emergency response coordinator. Staydive is a semi-submersible, that is, a partially submerged vessel floating on two parallel pontoons. It can be ballasted to varying drafts, depending on whether it's in position on site and operational or in transit. It's registered as a vessel and has the relocation facilities of a ship, with a maximum speed of 8 knots in moderate sea and wind conditions. It has 3 main deck levels, housing control rooms and personnel accommodation, with, on the upper deck, 3 cranes, the emergency access tower, helicopter facilities, and the submarine and its deployment facilities. As part of an efficient emergency response facility, Staydive has firefighting equipment which consists of 3 elements: a firefighting monitor system, a drenching system, and a gas detection system. The firefighting system comprises 4 main fire pumps which feed the 16 monitors, each of which is fitted with a long-range jet or spray nozzle. These can be controlled from the firefighting control center or operated locally as and when required. Together they can deliver 9,200 cubic meters of water per hour, while Staydive remains on station in up to 9 meter seas and 50 to 60 knot winds. The same control center also controls the drenching system, which is designed to cool the vessel when it's exposed to excessive heat. Its saturation spraying devices spray seawater continuously onto vulnerable areas, ensuring Staydive's operational efficiency and safety in an emergency situation. The access tower and its telescopic gangway on the upper deck fulfill vital functions when operating in yet another emergency service capacity, that of well killing. Together, they provide an extremely flexible and maneuverable facility for maximum platform access. The tower reaches 19 meters above the main deck, and the telescopic gangway can reach up to 50 meters above sea level, as well as being able to pivot 30 degrees up and 30 degrees down from its horizontal position. In the event of a serious blowout, a platform's own well kill equipment could be rendered unusable. In such a case, all the necessary equipment and materials can be swiftly deployed to Staydive, including special mud and mud handling equipment from the shore base at Lerwick. With the operation being controlled from Staydive, the special chemical mud which will kill the well is pumped under high pressure through kill lines running via the tower and gangway. The tower and its gangway also provide an alternative safe escape route for personnel in the event of forced evacuation. Staydive's self-contained medical center is probably the most capable offshore hospital facility in this sector. It's fully equipped, as is appropriate to its emergency response role. A state-registered nurse is on duty 24 hours a day, and there's always a qualified doctor on call in the field. The medical center has an isolation room, can cope with up to 7 people, and also houses a number of extra emergency beds which can be set up as required. Staydive's helideck is big enough to accommodate a Chinook and supplies essential operational requirements such as refueling facilities. In case of emergency, the helideck is equipped with the latest foam monitor system. The three cranes have lifting capacities of 25, 50 and 200 tons respectively. They're used for providing underwater operation support and for taking supplies on board, whilst also offering a topside lifting facility. Staydive's 200-ton crane has been used for several such topside lifts, including the change-out of a crane on Brent Alpha and the replacement of a section of flare boom on the Ork platform. It can also deploy the RMV, Remote Maintenance Vehicle, and is used for maintenance of the Underwater Manifold Centre at Central Cormorant, where it deals, for example, with change-out of valves, electro-hydraulic control modules, and the operation of the isolation valves. In the event of damage to a pipeline or the requirement to tie in a pipeline, Staydive can deploy its emergency pipeline repair system, incorporating a hyperbaric habitat that is located over the pipe. The habitat is dewatered, and divers then transfer to it from the diving bell to perform welding operations in a dry atmosphere. Staydive can move easily between locations, but once on site must maintain its position accurately. To do this, it uses its dynamic positioning, or DP system, which is monitored from a control room housing two computers, where the parameters of the exact position are entered. The computers are informed of any change of position through data received from various sensors, gyro compasses, anemometers, vertical reference equipment, acoustic positioning systems, and various radio-based systems. And appropriate commands will then activate up to 9 powerful thrusters, which maintain Staydive's position over the required worksite, keeping it to within 5 meters of the required location. The DP system has a backup redundancy system. Even with some of its 9 engines and/or thrusters non-functional, it can maintain full operations. Both the twin computer, multi-sensor DP system, and multi-thruster power system plus power generators illustrate the emphasis placed on safety and redundancy in the design of Staydive, thus ensuring both diver and vessel safety. Staydive provides a complete inspection, maintenance and repair service. It can carry out inspection of platform structures and nodes to give CP readings and warnings of pitting and cracks in underwater structures. It can supply anode retrofit to maintain platform and riser cathodic protection. It can detect when unsupported pipelines require span stabilization with grout bags. These are just some of the factors which can impede production operations and which can be identified by underwater work. They and many more can be dealt with efficiently, safely and quickly by using Staydive as an IMR vessel. Staydive's whole IMR service is organized and controlled by an integrated engineering establishment using advanced computer-based support systems. The primary system is USMIS, the Underwater Structural Maintenance Information System, used for managing the execution of underwater tasks. USMIS is able to handle the enormous volume and variety of data generated. It can support and assist in the demonstration of asset integrity and provide the underwater operations engineers with the data necessary to ensure effective work planning and therefore maximum performance. Another important facet of USMIS is that it retains knowledge of how things are done, and so ensures continuity in the wealth of experience and knowledge gained, despite inevitable staff changes. Staydive also has one of the largest and most advanced commercial diving systems in the world, capable of supporting in saturation up to 28 divers, who live in any of the vessel's 4 decompression chambers under pressures of up to 20 atmospheres, breathing gas mixtures of helium and oxygen. This enables diving to be carried out continuously to a maximum depth of 200 meters. There are also 2 3-man diving bells, which are lowered by 2 electro-hydraulic winches at speeds of up to 36 meters a minute, carrying 2 divers and 1 attendant. The diver's life support and communications are supplied to the bell via an umbilical. Cursor guide rails extend to the bottom of the port pontoon. They assist in stabilizing the bell during launch and recovery. Crosshaul booms extend 18 meters from the port side of the vessel and allow the bell to be placed as close as possible to the platforms, where divers can use the variety of underwater inspection tools and equipment available. There's also an air diving deployment system at the tip of the forward crosshaul boom, from which diving to a limit of 50 meters can be conducted. A manned submersible for platform and pipeline inspection can also be deployed. The PC-1805 submarine is a free-swimming, battery-powered vehicle with an array of photographic equipment which can take high-quality video and still photographs, records of any inspection task in which it's involved. In addition, it can carry a stereo camera system capable of recording three-dimensional images from which accurate measurements may be taken. Its two manipulators are capable of carrying out simple tasks, such as attaching shackles or releasing guide wires. The great advantage of having the manned submersible on board is that it can proceed with independent inspections whilst the diving bell is deployed on another job. Another of Staydive's facilities is the remotely controlled vehicle RCV-225, which is tethered to the vessel and receives its power and control through an umbilical. Not much bigger than a football, it's fitted with colour video and stills camera, and because of its size can get into restricted areas such as the nodes on steel structures. It's used for diver monitoring, where it performs a dual role, providing safety checks on the diver and also allowing the topside engineer to monitor the work in progress. And because the RCV-225 can carry out its work in the water for nearly 24 hours a day, it greatly enhances the efficiency of all underwater operations. At sea level, the air we breathe is made up of approximately 21% oxygen and 79% nitrogen at normal atmospheric pressure. As the divers descend below sea level, that pressure increases, and the oxygen and nitrogen they breathe start to act differently. The nitrogen dissolves into the blood and body tissues. If the divers then return to the surface too quickly, the dissolved gases, which are by now in liquid form in the body, become gas once more and return to the bloodstream, where they form bubbles and cause a condition known as the bends, which can be fatal. In addition, at depths greater than approximately 50 meters, breathing nitrogen under increased pressure causes a condition called nitrogen narcosis. Breathing oxygen at increased pressure also produces toxic effects. These problems were overcome by reducing the percentage of oxygen breathed and replacing nitrogen with helium. This mixture is called heliox and has no toxic effects. But it causes two other problems. The helium takes away body heat very quickly, and it distorts the diver's speech, making communication difficult. These problems have been overcome by supplying the diver with an external source of heat using hot water and incorporating speech unscramblers into the system. The bends problem is overcome by keeping the acclimatized divers in a controlled environment at constant pressure and breathing a constant oxygen-helium mix. This is saturation or SAC diving. When the diver is to return to normal conditions, atmospheric pressure is reached gradually, and the gases can slowly return to gaseous form, causing no problems. In the event of a vessel emergency, Staydive's hyperbaric escape chamber is capable of evacuating up to 28 divers under pressure. The primary function of Staydive is to ensure safety, obviously in the case of an emergency by firefighting, well killing, and providing an escape route and medical facility for personnel, and during normal operations by undertaking IMR work to monitor the structural integrity of a platform. So it's vital that all personnel on the rig should be aware that in providing this safety factor, the divers of Staydive are vulnerable and exposed to various hazards as they carry out their tasks. some of these hazards are obvious, others less so. Let's consider some of the sources of danger. Scaffolding and tubulars. Scaffolding poles and tubulars may drop straight to the water, but once submerged, they travel like a javelin and can end up a considerable distance from where they were dropped. When a diving operation is in progress, all scaffolding operations must stop, as must any transfer of tubulars between platform and supply boat. Mud dumping. Mud dumping destroys any visibility that the diver may have. It makes it impossible for him either to continue work or clear the work site safely before returning to the bell. Dropped tools. Anyone working above the water with tools or equipment could easily drop them. Anything dropped into the sea endangers divers. Where this might happen, there must be no work carried out above the diving site. Chemical dumping. Divers depend for survival on the hot water pumped down to them from the surface from inlets in stay dive's hull. Chemical dumping can contaminate the water, and this contaminated water could come into contact with the diver's skin. There must be no chemical dumping when diving is in operation. Fishing. Fishing lines are invisible in the water. They can entangle a diver very easily, and their hooks are potentially lethal. And that's not just fishing while diving is in operation, it's fishing at any time. Lost equipment, whenever it's lost, presents the same danger. There must never be any fishing from a platform. Inlets and outlets. In the immediate vicinity of the diving area, inlets and outlets can be very hazardous. Divers can be sucked into an inlet and trapped, or pushed by an outlet into danger, if either were to be suddenly activated. So any inlet or outlet near a diving operation must be closed during the operation and have a sign placed on it explaining why it's closed. All these musts and must-nots are vital. A momentary lapse could cause at least one unnecessary incident. Stay dive operates on the Shell Permit to Work system. That is, when Stay dive enters into the 500-meter zone of the platform, it must have a cold work permit before it can start on any platform inspection work. This permit stipulates the work that's to be done and also any precautions which must be taken. At the same time, Stay dive will normally be issued with a hot work permit. This permit covers any hot work that might be carried out on deck, and again it stipulates any precautions which are necessary. Certain underwater work, such as cutting or welding, may also be covered by the hot work permit. These permits are given only when the stringent rules which ensure the safety of personnel have been complied with in full. Shell Expro has a commitment to safety during underwater operations and to emergency intervention on our installations. For economies of scale, these commitments have been combined in the Stay Dive concept. The success and efficiency of the concept is evident when you realize the extent to which this vessel can provide all the IMR and underwater construction activities required to meet Shell Expro's program without any additional resources and costs. So as you can see, a successful and safe operation conducted using Stay Dive depends upon understanding and cooperation from everyone involved. Stay dive is an expensive asset to operate, and so any wasted time is costly. The safety of underwater operations is of paramount importance. Stay dive is committed to the objectives of the Target Zero safety campaign. And this safety guarantees maximum vessel efficiency, which in turn helps to maximize production efficiency. It's a continuous circle of awareness, cooperation and vigilance which makes Stay Dive such a valuable asset in every area of the North Sea operation.
Although life may have begun in the sea, it is a very long time since our ancestors left it. Evolution has made us completely unadapted to living underwater. The deep is a very hostile place for a human being. A diver's life depends totally upon his equipment. Not only that, most offshore diving depends on specialized personnel and equipment on the surface, continuously supplying breathing gas and heat. Divers are professionals. They require professional attitudes from other offshore personnel. Divers are required by law to possess certificates of technical proficiency and of medical fitness. And so their initial selection and training reflects the importance of both these aspects of diving.
Yeah, good communications inside.
The need for technical proficiency is obvious, for divers work in a totally different environment to everyone else. One important difference is the pressure, for apart from the lack of air, it is the increased pressure that makes the underwater environment so unlike everyday life. The pressure at the surface of the Earth is caused by the atmosphere, which extends into space for about 100 kilometers. The pressure at sea level due to all this air is the same as the pressure due to 10 meters of water, about the height of a two-story house. So, for every 10 meters descent, another atmosphere's pressure is exerted on the diver. The real problems occur not in going down, but rather in coming back up, because some of the gas the diver breathes dissolves in his body tissue and his blood. The amount of this breathing mixture that dissolves depends on pressure and time. The greater the pressure and the longer the time, the more is dissolved. If the pressure is released quickly, the breathing mixture comes out of solution in the diver's body in the form of bubbles. These block the bloodstream. The result? Decompression sickness, the bends. Mild cases cause pains in the arm and leg joints. Severe cases may lead to partial paralysis and even death. So divers need to stop or slow down on their way back to the surface. Then, as the pressure is slowly decreased, the breathing mixture has time to diffuse out from the blood. Over the years, decompression tables have been evolved. These indicate how long and at what depths or pressures divers must wait during an ascent. The tables depend on blood circulation, which varies from individual to individual and from day to day. So occasionally minor cases of the bends develop even when well-proven tables are followed. If this should happen, the diver must be repressurized in a compression chamber. Decompression follows by slowly releasing the pressure. So although it is only rarely necessary, divers must have access to a compression chamber for at least 12 hours after surfacing. A diver who has just surfaced still has a great deal of the breathing mixture dissolved in his blood and body tissues. Should he need to dive again, more restrictive, repetitive tables must be used to calculate his decompression times. Decompression is only one of the problems divers have to grapple with. Another is buoyancy. Normally, the human body floats, so divers have to weight themselves down. One consequence of this lack of effective weight is that most tasks will take longer underwater than on dry land. It also means that divers are extremely susceptible to all water movements, whether natural, such as tidal flow, or man-made. Suction from intakes for cooling and fire hydrants, as well as flow from ballasting operations and ships' propellers or thrusters, represent deadly threats to divers. The most dangerous place of all, however, is the surface and its immediate vicinity. It is then that divers are fully exposed to the forces of wind and waves, as well as the potential dangers posed by any surface operations. For short and comparatively shallow dives, a simplified bell is often used. These wet bells are not pressure containers. They allow the divers to stand in the wet with their heads in a bubble of air. Communications pass along an umbilical to the surface. Although divers are supplied with breathing mixture through the umbilical, they always carry an emergency gas bottle on their backs. How long this supply will last depends on the depth. A cylinder which would provide enough for 1 hour's breathing at atmospheric pressure will only last 10 minutes at 50 meters depth. And 50 meters is as deep as one can go breathing air, for there are serious problems associated with breathing air under pressure. Air is 21% oxygen and 78% nitrogen. Other gases make up the remaining 1%. At atmospheric pressure, referred to as 1 bar, 78% of the pressure is due to the nitrogen. So the partial pressure of the nitrogen is 0.78 bar. The partial pressure of the oxygen is 0.21 bar. Underwater and under pressure, the partial pressures increase. At 50 meters, the partial pressures are 6 times greater than at the surface. So nitrogen has a partial pressure of 4.7 bar. At these higher partial pressures, nitrogen narcosis begins to appreciably affect a diver. He feels intoxicated and his judgment becomes impaired, a state of affairs which reduces his efficiency and may threaten his life. Reducing the percentage of nitrogen in the air would solve this problem, but this means increasing the percentage of oxygen. Oxygen, at these higher partial pressures, starts to become poisonous. Eventually, a hyperoxic crisis occurs. Thus, a new gas mixture is needed, and heliox, a mixture of oxygen and helium, has been developed to fit this requirement. For diving at 100 meters depth, oxygen concentrations of about 5% are common. In most European countries, it is a legal requirement that heliox is used for all diving deeper than 50 meters. Although heliox has its drawbacks, it solves the narcotic problems of breathing air under pressures greater than 6 atmospheres. It does not solve the decompression problem. As far as a blood vessel is concerned, a bubble of helium is as bad as a bubble of nitrogen. As the depth increases, the decompression time increases. 1 hour's work at 50 meters requires nearly 2.5 hours decompression. 1 hour's work at 100 meters requires approximately 10 hours decompression. 1 hour's work at 150 meters requires about 29 hours decompression. For a given depth, decompression time will increase with working time, but only up to a certain point. Then, the blood and body tissue is saturated with gas. No more can dissolve. At 100 meters, this occurs after 6 hours. The decompression time is then 74 hours, just over 3 days. If the diver stays down at that depth for 5 days, he will still need 74 hours decompression. If he stays down for a month, the decompression time will still be 74 hours. To take advantage of this, the technique of saturation diving was born. Divers live under pressure in a hyperbaric complex for periods of up to a month. The pressure inside is roughly 1 atmosphere less than at their working depth. They're carried to work under pressure in a diving bell. So the only time the divers need to go through decompression is when they leave the hyperbaric complex at the end of their month's work. Food, clean clothes and other needs are passed to them through a small airlock. Appearances are deceptive. Although these two men are inches apart, it will take 3 days decompression before the divers under pressure will be able to step out into normal atmospheric pressure. In reality, they are 3 days travelling time away. It is the diving bell that transfers the divers under pressure that makes this system workable. Here, a diving bell is attached to a hyperbaric complex. Heliox is pumped into it until the pressure is the same as in the hyperbaric complex. Both doors then open easily. The divers enter one at a time. Once inside, the doors are closed. The bell is then lowered. On the way down, the inside door of the bell cannot be opened because of the comparatively high pressure inside. At the working depth, the internal and external pressures are equal, and the doors open easily. One diver, the bellman, always stays in the bell. The other divers are connected to it by an umbilical. This supplies the heliox mixture, heated water, and a communication link. The bellman checks the breathing mixture supply and maintains the divers' umbilicals at a length that enables them to work easily. The only reason he would ever leave the bell would be to help a diver in difficulties. On the way up, the procedure is reversed. The bell ascends without decompression stops to the hyperbaric complex. As the pressure there is similar to that in the bell, the divers enter without difficulty or delay. There they eat and rest. With this system, while the first team sleeps, another team continues the work. Outside the complex, the diving supervisor and his life support team also work in shifts. The divers are breathing gas containing 5.2% oxygen and the remainder helium. Apart from the enormous cost of heliox, it makes communication extremely difficult as it deforms speech. So much so that electronic unscramblers are needed. Inside the chamber, the divers have to lip read to understand one another.
Okay, fire away, mate. Couple of fried eggs, is that? Roger. Roger, mate. Okay, how would you like your rump steak? Come back?
I'd like it crystal.
No, sorry, I didn't get that, mate.
I would like it crystal.
You would like it quickly. Roger, roger, mate. Is there anything else you like?
Another big drawback of helium is its enormous heat capacity. The human body is accustomed to losing some of its heat to the air, but the heat loss in helium is 6 times greater than that in air. Even in room temperatures, the body could not cope with such a large heat loss, much less so in the temperatures experienced in cold seas. A diver's thermal balance must always be carefully maintained underwater. Overheating is as dangerous as underheating. All chambers and diving bells operating at pressures or depths greater than 50 meters are required by law to be heated. At depths greater than 150 meters, the diver's breathing mixture must also be heated. All diving bells carry emergency survival kits for each diver. Seen here, during a training exercise, the kit is used if the heating fails. As 80% of the heat loss is through the lungs, it includes a heat-exchanging breathing mask. The remaining 20% of the loss is through the skin. Even with this kind of insulation, the time a diver can survive in heliox without heating is very limited. Once a diver has managed to cope with the difficulties of breathing heliox under pressure, buoyancy, communication problems, and heat supply, he then has to begin to work. And the variety of tasks he is required to do is enormous. Divers are obliged to keep records of each dive they make, just as the diving supervisor must keep a log of every diving operation.
30. Just give us a quick count just while you're going down on your unscrambler.
In any deep diving operation, life support is the prime concern of the surface team. The diving supervisor is the man who, quite literally, has the life of his divers in his hands. A recent development which gives the diving supervisor eyes as well as ears is the remote-controlled vehicle, known to all divers as Snoopy. Equipped with a self-contained TV camera and lights, its thrusters enable it to travel in any direction underwater. Once there, it is operated by a team on the surface, usually under control of the diving supervisor. It is the diving supervisor alone who has the authority to start a dive and regulate its performance.
Yeah, go ahead, diver one. Roger, roger. Oh, Bell, can you just check if diver one's umbilical? He thinks he might have it snagged around somewhere, and see if you can pull it clear for him, please.
Diving can be stopped by him, as well as by the installation manager or the ship's master. In any emergency, the diving supervisor will always need immediate access to communications. He may also need medical help and extra facilities. He will be the only one who knows what he needs. Diving operations are very similar worldwide, but in the North Sea, some of the most extreme conditions are faced. So, on 24 hours a day standby at Aberdeen Airport are two small hyperbaric chambers owned by a consortium of 11 major oil companies. These chambers can be flown by helicopter and connected to any diving complex in the North Sea. Thus, divers under pressure, in need of urgent medical attention, can be brought back to the large hyperbaric hospital chamber at the base. Should an installation need to be evacuated, then any divers under pressure will need a means of escape, such as a hyperbaric lifeboat. It is the diving company's responsibility to have a contingency plan. Fortunately, it is rare that such eventualities have to be faced. Under more normal circumstances, there is still a great deal that everyone on an installation can do to help the divers. For safe diving practice does not end with the diving team. Everyone working in the vicinity of a diving operation needs to be aware of it. Divers working underwater are out of sight, but that should not mean out of mind. Many installations operate a permit-to-work system, but whatever the system, it is crucial that everyone is aware where and when diving operations are taking place. As well as everyone on the installation, all vessels operating in the vicinity must be informed. The correct signals must be displayed at all times, and heavy lifts must be avoided above divers and compression chambers.
Diving operations will be taking place at the northwest corner of the platform, and all personnel are advised to keep clear of this area. All over-the-side work must cease. I repeat,
divers are extremely vulnerable to debris dropped from rigs. Some debris can travel long distances underwater, so it's not just above the diving operations that it matters. Everyone hears the announcement that diving is beginning, but may later forget about it, although the diving operations may be continuing. Oxygen tanks in support of diving operations can leak, so no flammable materials of any kind should be kept near them. Fires have occurred inside pressure vessels, but only very rarely, and never when heliox mixtures have been used. If there is any doubt about any operation, the diving supervisor will be able to advise the installation manager. The diving supervisor will need all available weather and tide information. After all, his principal concern is the life of his divers, who are often performing tasks vital to the installation in difficult conditions. They need the awareness of everyone else working in the vicinity. Without diving, many developments offshore would not have taken place, or would have taken place much more slowly. Divers are an essential but vulnerable part of any offshore operating team. They are strangers in a totally hostile environment. With training and technology, they are able to work there. They don't, however, need any additional hazards. Give the diving team the help they need.